Greetings for the day. So this is Dr. Karthik, Assistant Professor, Department of EEE, Madanapalle Institute of Technology and Science, deemed to be University, Madanapalle. So today's topic is a comparative study of solar PV array configuration to optimize the power harvesting under different partial shading conditions. So this is our flow of presentation. So first one is introduction slide, equivalent circuit of solar photovoltaic system, different types of PV array configuration, different types of partial shading conditions, and specifications of Vikram solar PV module, and performance analysis, PV characteristics of waveforms, comparison table, and questions. So this is our introduction. So renewable energy electricity resources plays an important position in the power technology. So unique renewable power sources like wind, solar, geothermal, ocean thermal, and biomass could be used of era of the strength. So among these renewable energy sources, solar photovoltaic energy is increasingly more well like these days of because of its profitable in nature. So PV module is the essential gradient in a system which transforms sun energy into electrical power. So this is our equivalent circuit of a solar photovoltaic system. So generally we are using commonly used circuit model is single diode model we are using. So why we are using single diode model means it is used for helpful for the mathematical calculations. So this is our relation between the solar photovoltaic cells voltage and current is shown in the following equation. This is the equation of the single diode model circuit model. So this is our different types of PV array configurations. So there are 4 different configurations are there. One is series parallel, another one is bridge link configuration, third one is honeycomb configuration, and fourth one is proposed total cross tied configuration. So today we are going to discuss about different type of PV array configurations. So first one is series parallel configuration. So series parallel configuration is nothing but, so you can be able to see this is a very simplest way for the solar PV configuration method. So because it will be helpful to for the partial it will be helpful for reducing the power because of this partial shading conditions. So when you're speaking about the structure, so each module is the first connected in the series and which is formed to a strings, and then it is connected to a parallel. So this is our mathematical equation for the series parallel configuration. So you can able to see from the column point of view, first column that is completely we can say it as a string format. So PV1 to PV8, and correspondingly the eight columns are there. So based on the model of the series parallel configuration, we have divided the equations, we have framed the equation for this one, and you can see about the voltages also. VPV is equal to V1, V2 and V3 and up to V8. So we are finding the row voltages. And what is the power means? The power is nothing but the product of the voltage into current. So we have to multiply with the PV voltage and PV current. That is the series parallel configuration. So next thing we are going to do, see for the bridge link configuration. So what is the meaning of bridge link configuration means? So modules can be seen like a bridge like rectifier, but why means the array of the output voltages reduces if the number of PV modules exposed to different number of partial shading conditions. So this structure look like a bridge rectifier. So in this we can able to find the total amount of voltages, that is nothing but sum of the series voltages, and total amount of current, that is total output current, is nothing but the sum of the parallel current. So with the help of this configuration we can able to see the formula. IPV is equal to I1 plus I9 plus I17 plus I25 plus I33 I41 and I49 I57. So collectively we can say this 8 cross 8 into Vk. Similarly for voltage also, the array voltages, so V1 plus V2 plus V3 up to V8. So the current is nothing but this is the formula for voltage and this is the formula for current. And what is the power means? The product of the voltage into current. Next thing we will see for the honeycomb configuration. So honeycomb configuration you can see from the circuit diagram. So every 6 modules are arranged in a hexagonal like a honeybee structure. So each hexagon consists of a 2 sets of 3 series connected modules and which is connected in parallel. So see the formula for the same thing whatever we discussed for the bridge link configuration. The formula is the same thing. IPV is equal to I1 plus I9 plus I17 plus I25 plus I33 plus I41 plus I49 plus I57. So the whatever the formula we have used for the bridge link configuration, the same thing for honeycomb also. So you can see from the diagram itself it is looking like a hexagon structure. And next thing we can able to see, this is our proposed total cross tie configurations. So this configuration is also known as cross tie configuration. So which is helpful for reducing the partial shading conditions. And the modules are connected in parallel and these rows are connected in series. So total array voltage, that means that sum of the array, all array voltages, and total current is nothing but the sum of the module current with each row. So we can say able to see the IPV is equal to I1 plus I9 plus I7 plus I25 plus I33 plus I41 plus I49 plus I57. So we can say able to see find the voltages. So row voltage across the 8 rows are there. So VR1, VR2, VR3 up to VR8. So we can able to see the power is something but total amount of, that is the product of the voltage and current, that is something but the total power. So next thing we will discuss about the different types of partial shading conditions. So partial shading conditions in this concept whatever what we taken means artificial shading model we created. So normally the standard testing condition for the solar PV array is 1000 watts per meter square. So we have described 4 partial shading conditions. One is short wide, short narrow, long narrow, and center shading pattern. So if you see from each and every partial shading, that each and every shading diagram, you can able to see the unshaded modules are exposed to 1000 watts per meter square, and the shaded modules are exposed to different type of radiations. So you can see from the diagram itself 200, 300, 400, and 600, 700,000. So these are all the different irradiance level for the these four configurations, these four partial shading conditions. So this configuration, these partial shading conditions, which is implemented in a 8 cross 8 3V array, and which is implemented on a MATLAB Simulink model. So this is the analysis format point of view. So in this concept we are going to discuss about the 4 types of performance analysis. One is mismatching losses, another one is global maximum power, another one is fill factor, and another one is execution ratio. So what is mean by mismatching losses? So it is the difference between the sum of the maximum power of individual module under unshaded conditions and maximum power under partial shading conditions. So this is the formula for mismatching losses. And next one is fill factor. So fill factor is nothing but it is calculated by dividing the actual rated maximum power by the theoretical maximum power. So you can able to see fill factor is equal to numerator point of view P maximum and divided by VOC into IAC. That is mean that open circuit voltage and short circuit current. Next one is power losses. It is defined as the ratio of difference between the global maximum power point of the PV array at the standard test conditions and partial shading conditions to the at partial shading conditions to the GMPP at standard test conditions. So this is the formula for power loss. Next one is the final is execution ratio. It is defined as the ratio of maximum power at the global maximum power point and the maximum power at standard test conditions. So these are all the performance metrics for finding the these are all the performance metrics for a solar PV array configuration model. So this is our specification of the Vikram solar PV module. So in this we have defined as the different number of parameters. So maximum power, that is something but 335 watts, current at maximum power point 8.80 amps, voltage at maximum, that is a 38.1 voltage, and short circuit current is 9.35 amps, open circuit voltage is 46.5 volt. So in this previously what we discussed, it means power performance parameters. In that fill factor is nothing but maximum power point divided by VOC into ISC. So what we have to take means denominator we have to take it as VOC, whatever the value is coming here is a specification point of view, and ISC we have to take. So based on the specification we have simulated in the MATLAB model. So PV characteristics of a short wide and short narrow shading conditions. So you can able to see the uh, two shading patterns. One is short wide, another one is short narrow. So based on this all the 4 configurations, I propose the total cross side is the best one. So you can able to see from the graph point of view in a short wide pattern, you can able to see we got the power as maximum power as 10,718 watts. When compared to TCT, all the remaining 2-3 configurations are very less value we are getting. Similarly, if you go for short narrow pattern, we got answer as 16,066 watts for total cross-side configuration. When compared to TCT, our remaining 3 configurations are very less. So long narrow pattern also we have got the value as proposed TCT model as 15,450 watts. When compared to TCT, the remaining 3 configurations are very less value. Similarly, for center shading pattern, we got like 16,641 watts. When compared to TCT, these 3 configurations are very less value. So these completely um, uh, these com these completely these 4 waveforms we got from a MATLAB model, and this is the comparison table for the performance metrics. So as I already told that we have to analyze for different performance metrics for solar PV array. So we have divided as series parallel, bridge link, HC and proposed TCT. So in this you can able to see whatever the data, whatever the values I got from the simulation results, and through the some manual calculations we got the answers, and I make it as a tabulation point of view, you can able to see. So proposed TCT and proposed TCT for short wide and short narrow pattern for all the configurations. Similarly for long narrow and center pattern also we have taken like this. And what is the inference we got from? In short wide conditions, the TCT setup generated 10,718 watts of power. So that means that it is outperforming the other configurations by increasing the global maximum power by 5.18 percentage, 3.46 percentage and 3.81 percentage respectively. Similarly, in our short narrow condition, our proposed DCT model achieved a peak power output of 16,666 watts, with showing better case results with a decreased mismatching loss of 3134 watts and a high fill factor of 36.95 percentage. Similarly, under long narrow shading conditions, the TCT resulted in a GMPP enhancement of 6.02 percentage, 2.76 percentage and 3.95 percentage, which is compared with the series parallel, bridge link and honeycomb configuration. Similarly, for under shading center shading conditions, we got the highest power output as observed for the series parallel, bridge link and honeycomb and TCT setups are 15,823 watts. Like this it is coming 16,641 watts. So from the inference point of view, I want to conclude that our TCT configuration expelled across all the partial shading conditions, exhibiting the reduced mismatching losses and improved fill factors. So this is my publication. Actually, this topic is my one of my PhD objective. So this paper, this work has been published in the Indonesian Journal of Electrical Engineering Computer Science in the year of 2025. So any questions, you can just poll it in the forms, Outlook forms, and thank you.